everybody. Good afternoon. Welcome to the first Monday seminar in this autumn semester. It's my pleasure and honor to introduce our guest, Professor Gabriel Stanovsky from Hebrew University of Jerusalem. Professor Stanovsky came to tell us about his research, multilingual zero-shot transfer in low resource settings. Thank you for coming, and the floor is yours.
Yeah, thank you very much for having me. Thank you for the invitation to Prague. Thank you for your patience during setting up this whole thing. Yeah, so let me start with a very hopefully non-controversial statement that language is generally everywhere. So, for example, when we read the news, we deal with natural language. Here, if we look at medical records, we also use some natural language, so aspirin, stuff like that. If we look at legal documents, it's also written in somewhat natural language. Historical documents, which I will talk about in this talk too, and scientific protocols. All of them use some notion, some domain of natural language. And what I found interesting is that there are experts that work in each of these domains, right? And they have specific research questions that they want answered. And I think we're at a point in time where these different researchers at academia, so studying, I don't know, news and medical doctors and legal scholars, they're more or less aware that there's a thing called NLP and AI and stuff like that. And they reach out and try to answer these questions over large quantities of data using NLP models. So everyone here is familiar with NLP in general? Yeah, okay. And one more thing, if you want to ask questions, I'll be happy if it will be during the talk, whatever you feel comfortable with. I'm happy to make it a discussion. Feel free to stop me at any point. So in general, I thought that in this talk I can give you a taste of what my research agenda looks like, or what I would like the process of my projects to look like. So I would like to start from some extrinsic research question. So this is often through collaboration with scholars from the different fields that I mentioned. And what I like about it is that it involves real world text, so text that come in the wild from real distribution, and that there's very specific evaluation metrics that are used. So they want specific questions answered. They're not interested, for example, in, I don't know, improving accuracy or F1 or something like that. They're interested in answering some specific research questions that they have. And I think that university or academia is an excellent place for doing this kind of research. So as opposed to, for example, large corporations that usually have more resources than we have at the university. They don't often have this range of scholars working in-house, right? There's no Google's archaeology expert in-house. So I find it interesting that at the university, I get to talk with experts from all of these fields. And I think it's something unique that you can do at the university. And also, once you start working on these kind of research questions, I think that invariably you get to some deeper NLP questions that are more broad than the specific research question that comes from this specific field. So even if you study legal NLP, for example, then some more general language properties you'll have to deal with because you're working with real world texts. What I'd like to do today is to show you this kind of aspect, this kind of flow of one line of work, and how it started from a specific research question and led to more general questions in computational linguistics. So it will be a talk in two parts. The first part will be the extrinsic research question of how can we restore eroded parts in ancient Akkadian documents. So this deals with actual real world text from excavations. And the challenge is that we have a very low resource setting. And the main finding that we'll have in this talk is that multilingual pre-training, everyone here knows what pre-training is? Yes? Cool. That multilingual pre-training helps a lot, even in zero-shot settings. So this is the first takeaway that we'll see in this talk. And actually, when we did this work, which is very specific, right? This deals with Akkadian texts, which is a pretty niche topic, led to this more broader research question of how do zero-shot transfer works in downstream tasks. And this was published at the archaeology project was published at EMNLP. And as I said, it's an interdisciplinary work, so it has a lot of expertise from different fields. And this was led by my student, Corinne. And the second part of my talk would be exactly that, to look at multilingual pre-training and how choosing the different languages in pre-training affects zero-shot performance. And what we want to answer there is whether some pre-training languages are more beneficial than other languages. Is there a problem? Okay, than other languages. And a specific focus that we put in this work was to control for the amount of data that we have per language when we ask this kind of questions. And the main finding that we had here is kind of blood bank-like categorization of the different languages and how they interact with each other. And this was led by Dan Malkin and Tomasz that is here, and was presented at NAACL very recently in Seattle. Any questions so far? Oh. Okay, people online can ask questions. Okay, so let's dive through these two topics. So first, let's talk about can we restore eroded parts in Akkadian documents? Yeah, so this is a reenactment of the dialogue that we had with archaeology researchers. So Wayne and Nathan from the archaeology department. So they came to us. This is a reenactment. That didn't necessarily happen exactly like that, but something like this. So they said that when they transcribe ancient documents, so this is a very broad definition of a document, right? So it's actually a clay tablet that they excavate from the ground. So when they transcribe it to digital format, they have to deal with these missing parts. So you see that there's a hole here, and some parts are eroded here. And this is due to the time that has passed, right? So this was written in Akkadian thousands of years ago. So understandably, some parts got lost. And they wanted to fill those in using models. So we asked them, so how do you actually know how to fill in those parts, right? Because they're not there. How do you fill in those parts when you transcribe the documents? And they said that, well, we look at the different symbols around those missing parts. And we look at the surrounding context, and based on the context, they try to guess what was there in the middle, right? So does that remind you of something? Does this very, what? Something, yeah, of mass language modeling, right? So yeah, so that sounded very familiar to us. And it was nice to see that they came to us not knowing anything about current trends in NLP at all. And we obviously not knowing anything about this kind of research question. And apparently this is a huge problem. So there's tons of these clay tablets that are just waiting for people to transcribe them. And it takes a long time. So I think this is an example of how an interdisciplinary research question can help bring expertise from different fields, right? So we learned about this problem, and they learned that actually this kind of framing is very popular right now in machine learning, and there's tons of advances recently done in this field. So I guess none of you speaks Akkadian, right? Or someone does? Me neither, I don't speak Akkadian. And so just intro about the language a little bit. So it was used between 2500 BCE and 100 AD. So long time ago. And it's the earliest attested Semitic language. So in the same family like Hebrew or Arabic or Amharic. And it was a lingua franca of the ancient Near East. So it was very widely spoken and written. And it was written in cuneiform. So the tablet that I showed you before and that I'll show later, those markings are logographs similar to Chinese. So every word maps to roughly one or two such symbols, right? So the vocabulary for characters is very, very large. And this is the setting that we're working with. So apparently, the archaeology field is very digitally oriented, which is a pleasant surprise, because when they reached out to me and said that they have a lot of texts in these clay tablets, I was imagining like a folder with 10 pictures of different clay tablets. But actually, they're very working towards machine readable formats, which was kind of a necessary starting point for this project. So we worked with this corpus called ORAC that has around 2.5 or a little bit less, 2.5 million signs. So sign is what I said, the logogram. So this is not huge by any means, right? It's fairly low resource. So if you compare it to, say, BERT-based that has 3.3 billion words, it's orders of magnitude smaller, right? So this roughly corresponds to a word, more or less. So it's different scales, right? But we are at least hopeful that we can do something with it, right? Because there's recent work that works with this kind of scale of data. So the corpus that we're working on is composed of Akkadian text. This is the original transliteration of the text. I'll explain about that. And they also translate a portion of it. So we have this parallel corpus of Akkadian and English texts. Okay, yeah, so the process that those archaeologists do, they start from this beautiful tablet. So you see these markings. These are the cuneiform. And they want to digitize that, right? For posterity, right? This format doesn't hold for long. And they want to move it into a digital format that they also can query and read remotely and stuff like that. So the process that they take is they start with the actual tablet. They've actually shown me tablets that they have, which is pretty cool, or pictures of tablets that were found somewhere. And they start with reading a section of it. So apparently this has some markings on it that some people can read. And they start by digitizing it to UTF format. So apparently UTF, like the encoding, has symbols for the Akkadian cuneiform. So they start by just digitizing what they see. So here, there's almost no semantic interpretation, right? They basically just look at it and write what they see. That's what they do. But you can notice here that there's some special symbols, right? These X's. These mark that there's a missing sign here, okay? There's a hole here in the text that they couldn't read. After that, they do what they call Latin transliteration. This is what I think most of the experts work with. So this is a transliteration of these symbols, which you can read to some extent following Latin alphabet. And here you can see those signs persisting, right? So here there's more semantic interpretation that goes into here. So going from here to here, they do some disambiguation, but there's still these missing signs. And at the end, they try to fill in the missing signs based on the context. So they fill in these transliterated signs based on the context. So apparently, if you read this and you know Akkadian, then you know that this is one plausible completion of those missing signs. Does that make sense? Yes.
When I take the representation which is known,
That's an excellent question. Should I repeat it, or I can repeat it?
Yeah.
Oh, so the question was whether, or maybe let me rephrase it and say if I got it right. So how do they actually know how to transliterate this if this has been dead for 1,000 years and you don't know how to read it, right? So yeah, we were asking the same question. So do you have a guess, or someone has a guess? So yes, this is a presumed phonetical representation of this text. So if you read this, I don't know, say ina igalas, I wouldn't continue because I'm probably butchering it. But this represents how scholars think that this was pronounced. So how do they do that? What? Evolve? Yeah, language descendants. Other ideas? Yes.
Well, they also do bytetext.
Bytetext. Yeah. I think what I get what you're saying. So basically, if they have another text, like a text aligned, I don't know, with ancient Hebrew, right? That you mostly know how to pronounce, and you have places of names, right? Like, I don't know, Mesopotamia somewhere here. So you're assuming that they pronounce it roughly similar, and you start to build a vocabulary from there. But it's a guess, or famous people's name, like kings or stuff like that, that the pronunciation hopefully survived through the ages. So you know how you should pronounce that, and you try to break from there. But it's a good question, but not related to our work at all. Yeah. Yeah.
What is the ultimate point of?
Oh, I can hear you on the microphone.
The Latinizing this uniform signs. I mean, why don't we just stay at the Unicode level and treat these characters as the Chinese characters, for example? You cannot Latinize them because they bear this like semantic stuff in themselves. Yeah,
that's a good question. So the question is, why do we need this step? And the answer is that I'm not entirely sure. But this is something that this is the process that the archaeologists use in order to do that. And my guess would be is that there's a higher bar for learning this, right? You need to learn like thousands of characters. So it's basically like learning Chinese, right? And I'm not an expert at all, but I think that Chinese also has like a phonetic version, right? Writing system. So yeah. Yeah, for sure. But I think this has like a lower entry bar, but it's just a guess. But anyways, this is the field before we came. So it's not my invention to do this. But I just wanted to kind of lay out how they go from tablet to what they actually work with. So I've seen them working with this. I think it's easier to read. I don't know. So the diacritics actually means different stuff. So it's symbols, it's not Czech. I'm sorry for all the Czech people. It represents different stuff. So I think this is like markers for deities and entities and stuff like that. So it's super interesting, yeah. But what we dealt with was going from this thing to this thing. So they have a lot of texts that are in this format. And actually, this is the most time-consuming part because they need to do some processing to kind of infer what are the missing signs that go into it. So we wanted to build a model that does this part out of all of the other stuff. Okay, so modeling would be super simple one slide, which I think is the current state of NLP anywhere. So we start with this input and the assumption, and an important assumption that holds in real life is that we know the number of missing signs. So based on just the physical gap that was in the tablet, the scholars guess how many signs were there. So this is in the input. They actually know or think that there were 2 signs there, right? So this is an input to the model. Like take all of this sequence and predict 2 symbols. The model doesn't need to also predict how many symbols are missing. This is just a property of real world text. This is what they need. So, and I think this is an example of what I'm interested in. What are the actual use case that they're interested in, and not make it any more complicated or less complicated than what it needs to be. So we get this as input and the number of signs that we need to predict, and the output is what I've shown before. So we'll have 3 variants on BERT architecture. So as we said to all of us, this rings a bell for multilingual language modeling or mass language modeling. I spoiled the rest. So we have 3 variants. So one is monolingual. So we trained the BERT architecture from scratch on the BERT texts, right? So we had no representations for the symbols from beforehand, and we just start from scratch. So this is a monolingual model. The second one is a 0-shot model. So this one takes multilingual BERT without any fine-tuning, and we test it on how it can predict signs. And here we definitely benefited from the transliteration, right? Because we use the same scripts as many other languages in the corpus. And finally, we also have a model that combines these 2. So it starts from multilingual BERT, and we fine-tune it on Akkadian. Is all of that clear? Okay, so that's the modeling. And also, not super important, but we also used greedy K-beam decoding to cope with multiple symbols in a row. So if you have 3 symbols in a row, then we start a beam and we predict the K most probable, and then we keep that track of that, because otherwise it explodes the number of possibilities for for a sequence of tokens. The alphabet is pretty big, but you can get to like 5 or 6, right? And it becomes kind of exponentially bigger. But I guess it's true that for some small number of tokens, you can just exhaustively check all options. I agree. This is kind of an implementation detail. And just a note on metrics. So we use 2 metrics, hit at K and mean reciprocal rank. You can look at the formula, or if you know them, that's fine. We can look at a quick example. So for example, I ate musk for lunch. So I ate vegetarian dish for lunch, for example. So if the model needs to predict that missing token and say that the thing that was hidden is pasta, then hit at 1 would give you 0 because it will look just at the top one of the prediction, and hit at 2 would give you 1. Hit at 3 would give you 1 as well because you have the correct prediction in the top K here. Okay, that's hit at something, hit at K, and the MRR is kind of a smooth version of that. So you basically look at the position where the correct word was predicted. So here it's in the 2nd place, so you get 1 over that that prediction. So for the first, if you predicted in the top spot, you'll get 1, half, third, and so on. Is that clear? And just, I think for your question about the vocabulary, I don't remember how many words were there, but we did compute what is chance MRR just to kind of get a sense of where we are. And if you just output kind of a random ordering of the vocabulary, specifically for our task, for Akkadian, so the chance MRR, I think, is at 100%. That's the score that you'll get. So the word would be somewhere in the thousands of tokens, somewhere over there. Okay? Questions? Questions home? Okay. So we use the translated version. So all of the tokens are. That's a good question. We removed the diacritic for that purpose. So the question was, how do we deal with kind of how the vocabulary tokens, right? Those weird diacritic. So I think some of them would be because of like Czech, for example, but they would mean completely different things. So one implementation detail is that we removed the diacritics, but apparently you can read that almost as if you can fill that in. It's kind of a post hoc markings. Other questions? Okay. So let's look at the results, and this is going to look scary, but it's not too scary. So the corpus that we worked with had different sections or domains. So from letters from kings through something here is receipts, which I think is kind of fascinating that we have receipts from thousands of years ago, and that people kept track over these clays. But these are the different corpora that we have, or subcorpora that we have in ORAC. That's the corpus that we use. But for the purpose of this talk, we'll mostly focus on the aggregate. And these are the different models that we use. So one is a baseline that uses an LSTM model from Fetaya et al. From 2020 for a rather similar task, but we retrained it on our corpus. And these are the 3 corpora that I mentioned before. So this is the 0 shot, and this is the monolingual that was trained from scratch on Akkadian, and this is the combination where you start from a multilingual model and you fine-tune it on Akkadian. Okay, so you see that there's a lot of numbers, but let's focus on the more important ones. So 2 findings, I think, that we can take, and this is looking at single token evaluation. So the KBM thing is not even here. So one thing is that the results are really good. So if you think about this in terms of, say, MRR, this means that on average, the expected location of the best or the correct token would be in the top 1, right? It would, in expectation, choose the correct token in the first spot. And this is state of the art over all other models that we know for the task. So that's nice. And a second interesting finding that led to the second work that I'll mention is this result over here. So this is a model that wasn't trained on Akkadian at all, right? It didn't see Akkadian at any time. It wasn't trained on Akkadian at all. And you can see that it outperforms both models. So these two models that kind of perform rather the same, use the same data, right? They use only the Akkadian data. So I think this is also so interesting. So LSTM versus BERT, it's not that one is necessarily much better than the other. So the architecture didn't matter that much, but the data kind of led to similar results. But if you just use zero-shot approach, you get better results than training on Akkadian, solely on Akkadian. Does that make sense? Yes. So this model is MBERT, multilingual BERT, that we didn't fine tune it in Akkadian at all. We just showed it the text and asked how would you complete it based on the tokens before and after, right? So it's so it's not the best results, right? So if you do fine tune on Akkadian, you get much better results. But still, it's far from just random noise, right? So it's being able to capture something there. So we did the same face when we saw those results, kind of perplexed. And yeah, so I think why that happens is an open question, but I think it's evidence of cross-lingual transfer in mass language modeling, and maybe thanks to similar languages, right? So I mentioned that MBERT, for example, has Hebrew and Amharic and Arabic and other Semitic languages. So maybe those similar phonetic structures kind of helped it to predict those missing signs. But it's unclear, right? Because BERT has a lot of different languages in it. So it's unclear how they contribute. But more on this soon, because this led to the second project that I'll mention. Questions? What? Oh, great. Great. This is an excellent follow-up. Did you see my slides before? Great. Perfect. So how do they actually use it? So we actually wanted them to use it, right? That's the whole pitch that I gave at the start, right? I want people to actually use our stuff. So human evaluation, so all of the evaluations that we saw before are automatic evaluation. We knew what the token were, and we hit it, and we could test it over millions of tokens, right? But that's not the actual usage that we want to have. So we had different desiderata for human evaluation, and we wanted to account for three main things. So one, there's multiple correct predictions, right? So if I say I ate mask for lunch, and if you don't have enough context, then maybe hamburger or pasta or I don't know, what's a native Czech dish? Goulash. Goulash is Hungarian. So yeah, so all of these options are plausible, right? If I don't know, and it's kind of random what was the original token there, right? So we want to allow for that. And in automatic evaluation, it's kind of hard to do, right? How do you know that something is plausible? You just have one signal. And the other two factors are kind of very specific to the data that we worked with. So the annotators that worked with us, which were part of the project, per your question, are non-native Akkadian speakers, right? They speak Akkadian as a very foreign language. That's even, and they're I think we had 2 Akkadian-speaking people on the project, and they were 1% of all of the people that know Akkadian in the world, or something like that. So it was a very specific field, and even they don't know Akkadian as well as they know English, for example. So, and maybe lastly, there were also people that, from a kind of human-computer interface perspective, they kind of tended to believe what the machine showed them, right? I think there's some bias when you see some suggestions, you tend to want to accept it or maybe go against it. You have some bias because you know they're machine produced. So we wanted to take those into account. And for your question, how did we do the human evaluation? So this is how we evaluated the model using humans. So this is from the English portion, just so we can read it. So they saw these texts with the missing signs, which we masked randomly. So here you have to Inanna, spouse, blank, 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 temple administrator, I dedicated this, and they saw 5 options, right? 5 possible completions. And they could choose between 0 and 5. So either none of it is plausible or all of them are plausible. They can mark how many options they wanted. But behind the scenes, what they didn't know is that only 3 of them were model predictions. So say the ones in blue here. And we introduced 2 special destructors. So one was the gold, the thing that was actually there in the first place. And the other is some noise that we sampled, some random sequence that we sampled from somewhere. And the goal of this was to kind of estimate whether they tend to overbelieve the model or underbelieve it, right? So get these 2 boundaries. So if they mark this noise one as correct, then they tended to overestimate the capabilities, right? Just because they saw it as an option. And if they didn't mark the gold one, then maybe it's due to lacking knowledge in Akkadian or something, because it came from the text. They should mark that one. So we kind of have a lower and upper bound, and hopefully the real model performance is somewhere in between, right? And we also get how much they liked our model predictions. So using that, we can plot this graph that has error bars. You see that they're not symmetric because we can estimate whether they're under what percentage of the noise they're marking and what percentage of the gold they're not marking. Details are not that much important. But what you see here is this is on the x-axis is the number of signs that appear in a row. And this is on average how many of the predictions of our models they tended to accept. So we had 3 model predictions showed to them. And they could accept between 0 and 3. And you can see that for 1 token, they tended to, on average, accept between 1 and 2. So this is, we did the experiment also for English and for Akkadian over the same text because we had a bytext. And we can see that it deteriorates, but still it's close to 1 on average, even for 3 tokens, right? So this is the results from manual evaluation. Also, experts are using this right now to help speed up the transliteration. So hopefully we'll get more data about how useful it is, but I'm happy that it's something that actually we're trying to use it in practice. And I tried to get some sense of like scientifically say if this is good or bad, and I couldn't find any. If you have any idea how to compare it, I'll be happy to. But I kind of imagine it of some kind of a keyboard that you get suggestions, right? For completions, and on average, you choose between 1 and 2 here as plausible. I don't know, seems useful sometimes. I couldn't find any like more like scientific research that examines how often are these predictions clicked. I don't know. I was hoping to find something like that and kind of put it on the same scale, but couldn't. Okay. So this concludes the first part where we talked about one project that was very specific about Akkadian texts. And we saw this interesting research question that kind of arose from there about zero-shot cross-lingual transfer. And this is the second part of the talk. If there's any questions about the first part, I'd be happy to answer. There's online. Okay. No questions. Okay, so in the second part, I want to talk about cross-lingual transfer. And do people here know? Have heard about cross-lingual transfer in general? So in general, what we saw in recent work is something that is being done in other tasks in NLP is kind of picking up recently. So we start from multilingual pre-training, say on all of Wikipedia that has hundreds of languages. So this is, for example, multilingual BERT, and then you fine tune it for a specific language. Here it's part of speech tagging in English, for example, but you test it on a second language, so part of speech tagging in Hebrew. And this is kind of similar to what we did in the previous project, right? We pre-trained on a lot of texts, but we tested it on Akkadian, right? Which wasn't in the original test. And there's a lot of work trying to understand how does this happen. So for example, Turk-et-al questioned whether English is the best language to use here because you can use various languages during fine-tuning. And they found that English may not be the right one. And there's a lot of work looking at architectures, different architectures. So if you have shared words between L1 and L2, that would help this phenomenon. If you have shared parameters in the network for the different languages, that also helps. But when we looked at this, and also from this diagram, it seems pretty obvious that no one really tested this part of the equation, right? So you basically take for granted that you have some multilingual pre-training. Yeah, so what's going on here? That's what we wanted to ask. And if you notice, so the titles here are kind of inherently about the properties of languages, right? So English is not the right fine-tuning language, right? Because there's some property of English maybe, right? But what we found is that there's a big confound here. So we wanted to ask whether different pre-training languages affect downstream transfer, whether English is the optimal pre-training language, and whether we can choose better pre-training languages to improve zero-shot performance. So this is a diagram of the data in MBERT, in multilingual BERT, and the different languages in it, right? So if you want to say something inherent about the language, this seems like a pretty big confound. So there's 104 languages here, supposedly, in this pie chart. But this is the relative size of English within this corpus. So I think around 20%. And can you guess the next language? I can't, I don't remember. Chinese, Russian, German, French, Japanese, Arabic, and then 98 other languages that compose half of the data, right? So it's far from balanced, right? What we wanted to do is to balance this pre-training data to be able to say something inherent about the language. So obviously, multilingual BERT would try to represent English much more than it would try to represent Czech, for example, right? Because just so much of the data is English. So it would get better gains by better modeling of English, right? To do this, we subsampled 10 million characters from each language from a set of 22 different languages that you see here. And we kind of wanted to focus on different families and also different linguistic properties. So you can see that it's kind of mixed here. And we aim towards the smallest one in the data set, so this language, that has roughly 10 million characters, and we subsampled all of the other languages towards that language. So we get this more balanced pie chart, right? So this is how we would like it to look like. But I think one caveat that is important to me is whether this is a fair thing to do. So we claimed that MBERT was not balanced, right? But is this actually balanced? What do you think? Oh yeah, so you picked, what's the, so yeah, so. Characters, yeah. Yeah, and I think in a sense what I wanted, yeah. How do you? Yeah, how do you compress? Yeah, maybe that's a good idea. So you, yeah. So here we went by character, but I think it's not necessarily the correct approach, but at least it's more balanced. And the point is that, for example, maybe now we're skewing, actually English loses here because English per character has maybe less information, right? Because every word is probably longer than Chinese, right? And every word is definitely longer than Hebrew and stuff like that. So maybe a per character information in Hebrew or Chinese is much larger. So now we kind of skewed it towards other languages. And I thought that I'd find very easily works that talk about this, and I couldn't. So if anyone knows, I'd be happy to. But ideally, I'd like to get the same amount of information, right? But we did come up with this metric, which is kind of like what you're saying. So we want to see how many tokens are there divided by the number of unique tokens as a measure of information per language. And our data is correlated with that metric. And we use a single tokenizer over the entire data, which is something like compressing. So yeah, I think there's more work to be done here, but hopefully it's much more balanced than multilingual BERT. Here too, you use MRR. You already remember this example. And what we did is, so now that we have the balanced data, we want to see how different languages affect one another, right? So we came up with this directed bilingual MLM fine-tune score, which again looks scary, but it's not too scary. So we want to estimate how language S affects language T. So this is directional, okay? And we want to get a score for how much it affects it. And let's go through the score. So this is the performance of a model for mass language modeling that was trained bilingually on S and T and then tested on T versus, so this is a zero shot, right? Because it was tested on both and then, sorry, no, this is bilingual then tested on T, and this is monolingual model, right? So we want to see how much language T benefits from seeing S, right? So here it's just monolingual model and normalized by the performance of the monolingual model, and to see how much adding this S here will add it. Yeah, so in other words, we want this F score measure how much T gains from S. Was that clear or too confused? Fine. So once we have this data, we can compute all of these scores between the 22 different languages that we have, right? We can put all of the languages in this position and all of the languages in this position and get this huge matrix of 22 by 22 and get all of these computations when we translate an MLM model that sees both languages and sees the language by itself and kind of compute the score, right, over balanced data. Let's look at a concrete example just to make sure this point is clear. So for example, if we want to see how much French influences Arabic, we see here, for example, that if we get the performance on Arabic after seeing French, and this is the performance on Arabic without seeing French. So here actually Arabic loses, for example. Okay, so this number is lower than that number. So we get a score that is negative. Is that clear? Yeah. So we get a specific entry in that huge matrix. Okay, so that entry is negative. So negative means that actually French hurts Arabic. Okay, similarly, we can do for other languages. So here, it doesn't help between French and some language. French and German, so French helps German. Okay, 31, a positive score helps. And we can do so on and so forth until we fill an entire row. So this is how much French contributes overall to all languages in our data. Okay, so overall, we can get an entire score of how much French helps the 21 other languages. And we call this a donation score. Okay, if we sum over all of these numbers, we get this positive score overall. So overall, French helps other languages on average. Okay, so far so good. But we can also put French in the target position, right? So we can compute how much different languages contribute to French, right? And we can complete this column, right? So here, the zoom thing hides it, but we can see how much Arabic helps French, how much German helps French. So for example, that language, or say, I think this is Japanese helps French, right? And also Korean helps French, but other languages hurt. So what we see here is a couple of properties. So this is not a symmetric score that we get, right? So if language A helps language B, it not necessarily language B will help language A. And also varies pretty widely, right? So when you balance the data, you see these kind of patterns. And we can complete the entire metrics and just, if we want to get a recipient score, so how much was French helped by other languages, we can sum over columns here. So this we call a recipient score. So this is the complete chart for French, just as an example. Okay, so French overall donates that amount to pre-training, and it receives that amount from other languages. Yes?
You are training either on like all of the languages or on all of the languages -1 and you're
no. So every entry here is bilingual pre-training. Bilingual pre-training of like the X and the Y. And we want to see how much, say, French helps German. So we do that computation that the formula that we saw before. Like if we take German and French bilingual, but tested on French minus just French monolingual. So it's bilingual. Every entry here is bilingual. Is that? Yeah. Okay, but if you sum over the entire column, you kind of marginalize the language, right? So you get the score for a specific language in terms of recipients and donation. Okay, and we can do the entire process for all of the languages, and you can let the servers run for a month and get this entire huge metrics, and you can get donation and recipient score for all of the languages, right? So here, every column is summed, and here every row is summed to get the recipient and yeah, impressive, and the donation score. Okay, but this is a bit much to take in. So we can also plot them like this. So every language here is a point on this graph, and we can see recipiency versus donation. So for example, a language that would be here tends to donate because it's up in the score, right? So the score for donation, the summation over the entire row is positive. So it's above the x-axis. So this, for example, Arabic tends to donate, but on the other hand, it doesn't receive, right? So it gets hurt in general by bilingual pre-training. Okay? Kind of. So languages towards here, what would they represent? What do you think? Yeah, and here languages that tend to receive but do not donate, right? And just looking at this kind of gave Dan, the student, the idea of kind of a linguistic blood bank, right? So if you think about a blood bank and blood types, so you have this O type apparently that do exactly that. They donate, but they don't receive. AB do the opposite, and the others are kind of mixed. It's kind of loosely related, but it's a good framing, I think. Yeah, so this chart is one of the main takeaways. So languages exist on this spectrum in general. They tend to donate or receive from different languages in varying amounts. Okay, but you can also think of this. So basically we got this huge metrics, and then we asked what can we do with this amount of data and how can you actually process it. So one way, for example, is to look at this, right? And another is to think of this as an adjacency metrics, right? So you can think of every node here, every language as a node in the graph, and you can see, for example, this entry as the weight of moving between one language and the other. So you can draw all of this as a huge graph, like this one, and you can see all of the languages kind of plotted out and how they help each other or contribute to one another. So an edge here would be how much this language helps this language, right? And in the opposite direction would be how much this language helps that language. Okay, and Dan put up an interactive exploration where you can actually play with this graph and kind of look at different linguistic properties and see whether you can find these kind of clicks in the graph. Okay. Great. We can go through this pretty fast. We also wanted to see whether, so all of this talked about pre-training, but we also wanted to see whether this holds in downstream application. So we had that chart, right? That we saw that there's languages that tend to donate and languages that tend to receive. And we wanted to see whether those findings hold in downstream applications. So we built those pre-training sets that are composed around languages that tend to donate and languages that tend to donate less, and just random languages. And we wanted to see whether we see those same trends in downstream applications. And I think the short end is that we did to some extent. We don't need to go through the specific details, but here we see, for example, that the least donating, if we look at zero shot in name entity recognition and part of speech tagging, do the worst between the test. And if we look at recipiency, we can see similar things. So the most recipient one did better than the least recipient one. I'd be happy to talk more offline if you want. We also looked at specific linguistic properties to see whether they explain some of the donations and recipient scores that we saw. And I think a lot of multilingual work kind of struggles to find signal in these many numbers that we see. But in general, I think that shared script was helpful. So if you share script, diverse script could either help a lot or hurt a lot. And shared script is kind of a safe bet, I think. Whereas, for example, the hope was to see that kind of a linguistic family is kind of a click in the graph, and that all of the Semitic languages help each other. But actually, multilingual work doesn't work that way, and it's hard to find this kind of signal. And we didn't find like strong correlation between linguistic families. So maybe there's something else that's going on there. So there's more to explore. I think I'm on time, hopefully. If you have any questions about this work, I'll be happy to take them. Yes. It's MLM, so masked language modeling. So this notation means that we tested, for example, on bilingual, say French and Arabic. Okay, so the model saw French and Arabic during pre-training, and then tested on Arabic. Oh, it's MRR, so mean reciprocal rank. But this notation was kind of taken from other work. You can basically replace it with any other metric that you want for that specific task. So you do bilingual pre-training on 2 languages and test on 1 language, right? As opposed to just doing pre-training on a single language. What? You rank the different words and you get the relative position over entire corpus. Yeah. We did a lot of averaging in this work. Any other question? Okay, so I can conclude my talk. Yeah, so in general, I think this kind of shows the ideal flow for me for research agenda. So we start with a concrete research question in the real world, dealing with archaeological questions and something very specific and domain experts that are needed. And we saw evidence for zero-shot cross-transfer in low research scenarios. And then we saw that pre-training languages matter, which is one way to summarize the entire second part of the talk. And some are more conducive to zero-shot performance than others. And yeah, and in general, I think it's nice to start from this very specific question and kind of broaden out and say, okay, we saw some phenomenon here. How do we examine it more rigorously? And I think that when you deal with real world text and those stuff, that stuff tends to happen. So this is the ideal research line of work for me. That's it. Thanks for listening, and thanks for all my collaborators on these projects. Thank you.
Much for your very informative and very clear talk. So many questions have been asked already. So if there are some more, so please ask now. Please ask to the microphone.
Thank you for the talk. After seeing what we saw in your talk, what would you say it's like next bottleneck in doing zero-shot transfer? Like, is it still searching for the source languages, or is it something in the modeling, or is it something completely else?
So I think there are a couple of research avenues that can be followed. So one, I think that we weren't able to explain entirely. So we have this huge graph, right? And we weren't completely able to explain what linguistic properties actually affect that graph. So I'd be very interested in kind of drilling down into that and seeing whether there's some linguistic property that would predict zero cross-lingual transfer. I think that would be great. And also, I think it's somewhat too broad to just say that there's a single language, right? So English, there's English in the sports domain and in the scientific domain, in the news domain, right? So I'm more interested in looking at more granular, like how do different domains affect the language, and you can even look within one single language, right? So do this zero shot across different domains of the same language. So maybe that's 2 research questions. And the third is maybe how do you say I'm a application developer and I want to get the best combination for my specific application. How can I kind of mix the languages such that I get the best performance? Because out of all that messy table with tons of numbers, what I get out of that is that the choice of pre-training language, some of them perfect. So maybe if you want to get the exact correct combination, imagine someone wants to develop a specific application, they input a set of criteria. I want it to work for English in the sports domain, and kind of the model kind of chooses the correct combination of pre-training and fine-tuning and gets the optimally performing model. Is that a good answer?
Thank you.
Okay. Someone.
Have you tried to do any, at least like preliminary analysis on how probably the groups of languages may improve or decrease the performance of some new language? I mean, like not trying to measure how French has an impact on Arabic, but like how Romance languages or how all the Latin languages improve the performance of Arabic.
Yeah, it's a good question. It was on our list, but we didn't get to it. So for example, you can imagine that in this graph, instead of having a single language, like you'll have all of the Semitic languages and how much they affect. Yeah, definitely. But we kind of ran out of compute at some point because we ran so many experiments. Yes, I mean, you can just deduce it from the graph maybe, but you're not actually pre-training on the entire languages, right? We've been thinking about it, but then you'll have to kind of.
Yeah, actually, there might be some effect of synergy also.
Definitely. So that's another research avenue. Kind of take this approach, but have linguistically motivated groups of languages, right? Yeah. And you can't, I think, you can't necessarily deduce it from those results because you don't have the synergy that you mentioned. Yeah, but you balance it in the same approach, right? Yeah. You can't readily see it from this graph, but yeah, definitely it's something I think it's really interesting to try out. Yeah.
Some more questions. Give counsel.
Thank you very much.